In this lecture, we are going to motivate the use of sequence models for modeling stock returns. So let's start by recalling one of the themes of this course. This course is not about making perfect predictions, and in fact, a lot of the course is about why you cannot make perfect predictions. It's about understanding why predictions like these, which use LSTMs, are not useful at all, and not only that, they are worse than simpler models like ANNs and ARIMA. Most of this course was getting you to recognize what you cannot do, so the question remains, what can you do? And I hope you'll recognize that this section partially answers this question. Okay, so earlier in the course, you'll recall that we modeled stock returns. We noted that, although initially they look like they might be normally distributed, they are not actually normally distributed. Instead, they have fat tails and skinny shoulders. Two ways we modeled this kind of distribution was with the t-distribution and with Gaussian mixtures. We recognized that when we drew samples from two Gaussian distributions with different variances instead of just one, we got the fat tails we were looking for. But we also recognized that stock returns are not quite stationary. Stock returns exhibit what is called volatility clustering. That is to say, when we see high variance, it is usually surrounded by high variance. When we see low variance, it is usually surrounded by low variance. This clearly violates the definition of stationarity, although the statistical tests we used for measuring stationarity were not able to detect this. So this section on sequence modeling is all about answering the question, can we model this time-dependent volatility? In this section, our model of choice will be the hidden Markov model, or the HMM. We looked at Markov models earlier in this course when we discussed the random walk hypothesis. This is similar to that, except now, our Markov model is over a set of discrete states. But before we even discuss Markov models or hidden Markov models, I want to discuss graphical models. This will help us understand the structure of our model and how we can build it up from simple to complex. So earlier in the course, we looked at the Gaussian mixture model. Let's review that again, but in the context of a graphical model. In the graphical model, it looks like this. We have some hidden cause or latent variable called z. This is represented by an unshaded node. Unshaded means that we do not observe this value. Then we draw an arrow going from z to x. X represents the stock return, or the observation that we actually do see. Since we do observe this, it is shaded in. Note that some books or resources may reverse this convention, or they might simply use different colors and not shades. Either way, the important thing is that you remain consistent in your own work. But don't freak out if you find out that different resources use different conventions. Okay, so let's think about the physical interpretation of this graphical model. I like to think of it as God flipping a coin. If the coin lands on heads, then we sample a return from one Gaussian. If the coin lands on tails, then we sample a return from a different Gaussian. Of course, God can't tell us the result of the coin toss directly, so all we get to see is the sample from the Gaussian. In our case, that's the stock return. Okay, so that's the physical interpretation. God flips a coin, and then the clouds decide how much it's going to rain based on whether the result was heads or tails. If the result was heads, the clouds get very excited and rain a lot, and if the result is tails, the clouds are very relaxed and decide not to rain that much, if at all. We can only measure the amount of rainfall, but we cannot measure the result of God's coin flip. It also helps to think of other kinds of graphical models to build your intuition. Here's a very simple one, representing your own coin toss. In this scenario, all we are concerned with is the result of the coin toss, whether that's heads or tails. Since you can observe the result of your own coin toss, this node is shaded in. Furthermore, there is no process involved with different random variables. The only random variable is the coin toss result itself. Therefore, our graphical model is just a single node without any edges. Here's another graphical model known as naive Bayes. In this graphical model, everything is observed. To give you an example, suppose we are trying to predict whether or not an email is spam. So that's what Y represents. In supervised machine learning, we call this the label. In our model, this Y has a direct influence on certain attributes of the email itself. Let's suppose that, in this simple case, we are looking at two attributes or two features. Feature number 1 is whether or not the email is from someone in your contact list. We'll call that X1. Feature number 2 is whether or not that email contains the phrase, "make money." We'll call that X2. So you can imagine why the label has an effect on these probabilities. If Y is spam, then we expect the probability of the email being from someone in your contact list to be lower. If Y is spam, then we expect the probability of the phrase "make money" to be higher. Okay, and we can measure these probabilities using simple counting as usual. The important part of this picture is that you understand how each of the nodes affects the others and the physical interpretation. The direction of influence is the direction of the arrows. Here's another interesting fact. If we compare the Bayes classifier with the Gaussian mixture model, we can see that they essentially have the same structure. Note that in this case, this is a non-naive Bayes classifier, whereas on the previous slide, we were looking at naive Bayes. In this case, the entire observation is wrapped up in a single vector x, and it's not possible to separate it into x1, x2, and so forth. In any case, don't worry so much about these details, although if you want to learn more, I'll be happy to provide you with references on the Q&A. What is important to recognize is that these have the same structure. In the Bayes classifier, we have a coin flip called Y, which we are allowed to observe, and then this produces an observation X, which is dependent on Y. In the GMM, we have a coin flip called Z, which we do not observe, and then this produces an observation X, which is dependent on Z. In both cases, our observation distribution was dependent on the result of a coin flip. The only difference is that, in one case, we were not allowed to observe the result of the coin flip. Finally, note that the arrows represent conditioning. So if a node does not have any arrows going into it, it's represented by a marginal distribution. That would be either P of Y or P of Z. Then, since we have an arrow going to X, the next distribution would be P of X given Y, or P of X given Z. This makes it explicit that the distribution of X is a function of Y or Z. Okay, now that you understand the basics of graphical models, let's look at the Markov model. The Markov model is where we have a set of states, and the probability of moving from one state to the next depends only on the state that you came from, but not any state before that. To give you a realistic example of this, suppose you are modeling your state of sickness and health. So you have one state, which represents being healthy. You have another state, which represents sneezing. When you are sneezing, it could be the case that you are about to catch a cold, or your immune system may be able to fight it off, and you could go back to healthy. Finally, you have another state, which represents having a cold. Now, we also have associated probabilities for each of these arrows. For instance, the probability of being healthy and staying healthy is 0.99. That is to say, if you're healthy one day, it's very likely you will remain healthy the next day. Of course, there's a small chance that the next day you may develop some sneezing, which might signal an oncoming cold. Perhaps the probability of going from healthy to sneezing is 0.009. Finally, there is a small chance that the next day you may develop a full-blown cold. The probability of that is 0.001. Note that these three probabilities sum to 1. Now let's turn our attention to the sneezing state. In this state, let's say that you have a pretty even chance of just going back to healthy the next day or becoming sick the next day. So the probability of going to either state is 0.5. Note that the probability of going back to itself is 0, since these probabilities must sum to 1. Finally, let's look at the state where you have a cold. In this state, you have a pretty high chance of still having the cold the next day, at 80%. You also have a decent chance of getting better, at 20%. So why does this make sense? This is because when you have a cold, there is a pretty good chance it will last more than one day. Therefore, the probability of staying in the state on the next day should be greater than 50%. However, it should not be as high as going from healthy to healthy, because typically we spend much more time being healthy compared to having a cold. So hopefully these probabilities make sense to you, and hopefully this helps you understand what a Markov model is. The really important thing to notice about this is that whenever we decide which state to go to next, the probability depends only on what state we are in. For example, if we are healthy today, we know that the probabilities for tomorrow are 0.99, 0.009, and 0.001. This is the case regardless of where we were yesterday or the day before that. That's why this is a Markov model. Now, I just realized that this diagram may be terribly confusing. Not because it's confusing by itself, but because it is not represented as a graphical model like the diagrams we were looking at earlier in this lecture. Note that for those graphical models, each node represented a different random variable, and the arrows represented the conditioning of those random variables. In this current diagram, all the nodes represent the same random variable, that is your state of health, and each arrow represents the probability of going from one value of that state to a different value. Okay, so how would a Markov model look in graphical model form? In this case, your state of health on each day, or each time step, is a separate random variable. So we can call the state of health on day t, x of t. So we have x of 1, x of 2, x of 3, and so forth. Notice a few important things. Firstly, each x of t depends only on the previous day, x of t minus 1. That's what makes this Markov. X of t does not depend on any day before x of t minus 1, nor on any day in the future. Otherwise, we would have to draw arrows connecting those days. Furthermore, notice that each node in the graphical model encapsulates the entire distribution and set of states. So x of t can be healthy, sneezing, or having a cold, but we don't actually see those on this diagram. Furthermore, we also cannot see the type of distribution. Each x of t could be a discrete random variable with 1000 states, or it could be a continuous random variable. But either way, this diagram does not tell you this information. Finally, note that unlike the previous diagram, these arrows do not represent the probability of transitioning from one state value to the next. These arrows represent dependencies, just like the graphical models for GMMs and naive Bayes that we looked at earlier. As another side note, recognize the fact that what we described previously is a discrete state Markov model. That's why we can draw it as a diagram with nodes and arrows. What we drew was a state transition diagram showing each of the individual discrete states and the probabilities of transitioning. This is opposed to the random walk model we discussed earlier in the course. That was also Markov, but that was a Markov chain over continuous states, of which there are an infinite number of values. Therefore, the Markov property is still true, which means that each state depends only on the previous state. However, it's not possible to draw it in the same way, since our state space is continuous. On the other hand, it can still be represented by a graphical model where each node can represent any kind of distribution and each arrow represents a statistical dependency.